All right, this is Mr. McCord's chemistry class, Unit 8. We're looking at the ideal gas law. Okay, so there are a couple important things we've got to hit in this video before we get to the problem-solving math stuff. So let's start over here first. When we work with gases, since there are so many properties at play that can change and change each other, like pressure and volume and temperature and amount of a gas, it's helpful to chemists to have a set of conditions that we refer to as sort of standard. So we're all on the same page of what we're talking about. So chemists use something called STP to describe standard temperature and pressure, right? Standard temperature is simply just 0 degrees Celsius, or in Kelvin, like we'd want it to be. That's 273.15 Kelvin. Right? Since we can deal with a couple different pressure units, we can have a couple different ways we say standard pressure, but they all mean the same amount of force pushing. It's just different units to describe it. Okay? Standard pressure could be 1 atmosphere, or 101.325 kPa, or 760 millimeters of mercury, or mmHg. So again, all of these are equivalent pressure values, just different units of showing that. Okay. Now, because of the way that we treat gases, ideally, we simplify a lot of stuff about how real gases work, because the math comes out close enough for us to just roll like that. So when we deal with the kinetic molecular theory and say, doesn't matter whether the gas is a molecule this big or this big, we treat it the same way. We don't consider it wavering or attracting to things, or the volume taking up its own space for the particle compared to the container of the gas. When we make those simplifications, we should be able to predict other parts about the gas without having to go into the lab. All right, we should be able to calculate at standard temperature and pressure, if I have this much gas, how much volume should it take up? Or if I have standard temperature and pressure and I have this volume of gas, how much amount-wise do I have of that chemical? Okay, so with those assumptions, standard temperature and pressure tell us that if we have 1 mole of gas, that should fill up 22.4 liters of volume. Okay, and this is a nice, nifty kind of relationship that can save us some time. If we're doing our calculations or our experiment at standard temperature and pressure, then we know kind of a relationship between those, no matter, again, what kind of gas we're dealing with. Now, in the real world, chemists maybe don't always like to do experimentation at these conditions because 273.15 Kelvin is really cold, but if you're doing it in a container at 0 degrees Celsius, then maybe it's not going to be so bad. Okay, so this is known, this is tested, all right, and this is something that kind of comes along with Avogadro's law. Okay, let me fix this one right here. Okay. Now, also with what we've been talking about with the gas laws so far, we know some things about how pressure and volume and temperature and amount of a gas relate to each other. Okay, so we've been able to crunch some of those together into the combined gas law, but we haven't still put everything together in one singular gas law. We also haven't, taken into account how do we calculate something for a gas when it's not changing. When I just have something in a container, I'm leaving it there, I've got a pressure and a volume and a temperature. I want to use that to figure out how much gas is inside, how many moles of that chemical I'm dealing with. So we need a final gas law that we cover in this class, one gas law that's going to tell us all of those things connected together, volume and pressure and amount and temperature, and also give it to us in a single moment instead of a before and an after. Okay? That is going to be the ideal gas law. Now, to make the ideal gas law, we're going to take a little bit of both of these things. Okay? With the relationships we have so far, volume and pressure go opposite directions. If volume goes up, pressure goes down, but volume follows the other stuff in the same direction. So we have a directly proportional relationship with volume and amount and volume and temperature, and it's an inverse proportion with volume and pressure. This little weird kind of bad fish looking drawing is a proportionality sign. We use it in math sometimes. So volume is proportional to 1 over pressure, or volume is proportional to an amount in moles. So if we clump that together, we can try to make a gas law that puts all of that together, puts together volume and pressure and temperature and amount. But we run into a problem, because this looks fine. I mean, we've got pressure on bottom, because they're inverse. We've got amount and temperature on top, which is good. But when we go and plug the numbers in, knowing this stuff, it doesn't work out. If I know that 1 mole of gas should fill up 22.4 liters of volume, and I try and plug that into this, 22.4 liters of volume, 1 mole of something, some gas, all right? And I put it at standard temperature and pressure, like this all says here. So I'm just using atmospheres in this case, and my temperature, 273.15 Kelvin. That's not right. That doesn't come out to be the same thing. It's not 22.4 on both sides. Since we can use different pressure units for standard pressure, I could try switching in. Maybe it works for kPa. You plug in 101.325? No. You try 760 mmHg? There's something missing from this equation. There's something that's going to bring it all together, and to make the ideal gas law, to talk about, ideally, how a gas has all these 4 properties that relate together, we need one more part of this equation that's going to stick in right here. Okay? That thing that we're missing has its own symbol. There, here. Right? That thing that's missing is symbolized by R, a big R. Right? And we call that the gas constant. That's our missing piece. Okay? A constant just means it's a number in science. It doesn't change. Pressure is variable. It can change, depending on what we put the gas through. Same with volume and temperature and amount. But this gas constant will always be the same number. Kind of like how we have specific heat capacities that we would just plug in for different substances. Except this isn't even for different substances. This is just overall. It is a number that we plug in. If you get into advanced chemistry, this shows up in other places too, just besides gases and stuff. It goes everywhere. So this is kind of an important thing, okay? But this ties up a lot of the stuff that we were missing here. The gas constant is a number that basically fixes our math to make this equation work. Okay, so the ideal gas law can link together all of our pressure and volume and temperature and amount of a gas to help us figure one of the missing pieces out in a single moment instead of before and after. Now, we've thrown in this piece that we were missing, the gas constant, big R, right? But this is kind of messy the way it's written out. So to make the math setup easier, usually things get rearranged and look something like this instead. This is how you will usually see the ideal gas law written. That being said, you can rearrange stuff however, but this is kind of the classic way we set it up. So we've got 4 variables in here and our one constant, the R, right? If we want to solve for a missing pressure, we just get P alone. If we're looking for missing volume, we get V alone. If we're looking for how many moles of gas we're dealing with, we get N alone. If we're looking for the temperature of the gas, we get T alone. It's just algebra from there. And since we don't have as many things on bottom here, using the ideal gas law can actually be a little bit easier math-wise. But there are a couple more things that you can keep in mind, tricks to kind of get everything to work right. So we're going to kind of go over some of those. Okay, so first off, again, you will see STP be brought up with the ideal gas law kind of problem pretty often. So it's good to recognize what it is and, all that kind of stuff. So at STP, again, temperature, at standard temperature, it's just 273.15 Kelvin. Pressure is 1 atmosphere, or if you're working in kPa, 101.325 kPa, or if you're doing mmHg, 760 mmHg. Okay? Now, if you aren't given a pressure unit, you can use any of those. If you're told, hey, this is at standard pressure, well, which one? Any of them. You can pick 1 atmosphere or 101.325 kPa or 760 mmHg, as long as you pick the right gas constant to go with it, which we'll kind of talk about here in a second. Okay, so otherwise, you can just kind of look out for if the problem tells you a specific pressure to work at. Okay, as long as we have standard temperature and standard pressure, one of those three, okay, that means that 1 mole of gas must fill up 22.4 liters of volume. The ideal gas law states it. Okay? Otherwise, something's going wrong. Now, we can still work with gases not at standard temperature and pressure. This is just a set of conditions we can lay out. So the ideal gas law can work with STP. It can also work when you're not in STP, when you don't have 273.15 Kelvin as your temperature, or you don't have one of these pressures for your pressure. As long as you don't have one of those conditions, though, either the standard temperature or the standard pressure, we can't use this. This is only true as long as you are at STP. If you're not at STP, you are free to use the gas law as it is. Just make sure you don't make this assumption. Okay, this is only true at STP. Okay, otherwise, whatever temperature and pressure you're at when you're not at STP, we just plug it in and work out the math basically the same way. Okay, so the ideal gas law can be used in any set of conditions. It doesn't just have to be at STP. It's just kind of a convenience thing. Okay, now, in order to figure out what to plug in for your R, like I said before, R is a constant. It's the gas constant. Okay, so that means it's just going to be a number we plug in. It's not going to change from problem to problem. But we do need to make sure we pick the right one to match our pressure unit. Okay, so if you are using atmospheres for your pressure, you want to use this number for your R constant to plug in. That will fix the math to make the ideal gas law work. Okay, if you're using kilopascals, you want to use this guy. If you're using millimeters of mercury, you want to use this guy. Okay, so if you are doing a problem and it's like, you're in a pressure of 3 atmospheres and it gives you a temperature of 300 Kelvin, you're dealing with 1.5 moles of gas, how much volume does that take up? Okay, well, if you want to solve for V for that volume, you've got an R constant to plug in. We're plugging in 0.0821, where the R is, right? And this unit shows everything else that has to go into that problem. So we have to have atmospheres for our pressure, we have to have liters for our volume, we have to have moles for our amount, and we have to have Kelvin for our temperature. Now, Kelvin temperature is something we were already strict on, all right? Liters was something we were a little bit flexible on. Like, you can use milliliters if you want. Not anymore. We have to have things in liters for the ideal gas law, okay? Volume has to be in liters for the ideal gas law. Volume has to be in liters for the ideal gas law. Temperature has to be in Kelvin. Match your R constant with whatever pressure unit you're using. Okay, so if you're using kilopascals, we use 8.31 as the number we plug in, and our unit shows that we're using kilopascals, we're using kPa. Again, volume is in liters, amount is in moles, temperature is in Kelvin. Okay, and finally, if you're using mmHg, the number you plug in for R is 62.32. Right, bigger volume or bigger number for pressure, so bigger number for your R constant. Pressure is in mmHg, volume is in liters, amount is in moles, temperature is in Kelvin. Okay? Now, if you're trying to keep track of units, as a good chemist does, and you're trying to cancel things out, this can make things really nasty and annoying. So if you need to, always just know that the units that you are needing for the problem are all contained in the gas law. If you're solving for pressure, you better end up with the pressure unit. Okay? If you are solving for volume, you better wind up with liters. If you are solving for amount, you better wind up in moles. And if you're solving for temperature, you better end up with Kelvin. Okay, so if you haven't been too hot on trying to cancel units as you go and make sure your math works out, then do the algebra the way you know works, and then pick the unit that fits best. It's better to do it that way than to over worry and stress about, oh, I don't know if that cancels and why is that on bottom? If you get stuck, just do your math as usual and say, hey, I'm solving for pressure, I'm picking a pressure unit. Okay? If you're good with units, though, all power to you, but if not, don't stress about it too bad. All right, let's do an example with the ideal gas law. So say I've got a can of soda like this, and I want to figure out the amount of gas, like CO2, carbon dioxide, that's trapped inside this can, right? Let's pressurizing it. Now I'm going to take some liberties and say that the pressure is only coming from the gas itself and not from the liquid that's also inside the can. Okay? So the can has a volume of about 355 milliliters, according to the can. Well, we can't use that in the ideal gas law because it's got to be in liters. So we're going to convert that. To go from milliliters to liters, we're moving 3 decimal points to the left. 3 spots to the left. So really we're dealing with a volume of 0.355 regular liters. All right. Our pressure inside the can is rated to be about 300 kPa. And this is what we're trying to find. We have to pick a gas constant. Since we're using kPa, since we have that pressure data there, we should use the gas constant that goes with kPa. The gas constant for kPa is 8.31, and the units are kPa liters over mole Kelvin. All right? And our temperature that our can is at in this room is about 23.5 degrees Celsius, a little toasty. But we can't use that either the way it is. We got to change that into Kelvin. So we have to take 23.5 plus 273.15. All right, in my head, it's going to be 96.65. Check that. So our temperature should be 296.65 Kelvin. So all I have to do is plug all this into the ideal gas law, this guy right here, and solve for my moles of gas. So 300 times 0.355 should be equal to N, our number of moles, times our gas constant, 8.31, times our temperature, 296.65 Kelvin. All right. So what I'm going to do is kind of ignore the units while I'm doing the math, because I know it's got to come out in moles if I'm dealing with N. All right. And otherwise, it gets really messy trying to cancel out units. So let's clean this up a little bit. Okay, that's a little bit better. 300 times 0.355 should be equal to N times 8.31 times 296.65. So if we are trying to solve for N, we've got to get it alone. I'm going to condense these guys first, just because I like to clean up the math. But if you like to rearrange stuff first, that's also fine. So I'm going to take 300 times this 0.355. And I'm going to take the 8.31 times this 296.65. All right, so this part over here I got multiplied to 106.5, and my 8.31 times my 296.65 gives me 2,465.16-ish. Okay, so my last step is to get N alone by dividing off this multiplied term here, this 2,465 number. Okay, so those will cancel out, go away. So I should just be left with N. Right? And N should be equal to 106.5 divided by 2,465.16. All right, I got about 0.043, all right? And since I'm looking for N, I'm looking for moles, so my unit is going to be moles. All right, 0.043 moles of gas are what's giving this can of soda its pressure. So basically just more algebra stuff. Okay, let's do another example. Let's say we've got a balloon that is filled with 16 grams of carbon dioxide, CO2. We're keeping it at standard temperature and pressure. Right? We want to figure out what the volume of the balloon is while it's kept at STP. Okay, well, our gas law is PV equals nRT. So let's plug in what we have and see how we should shake out the math. Okay, well, standard pressure for P could be 1 atmosphere, or it could be 760 mmHg, or 101.325 kPa. But honestly, if I want to make my math easier for myself, I'm just going to pick the 1 atmosphere, and I'll pick the right gas constant to go with it. Usually doing math with 1 in there instead of 760 or 101.325 is way easier. So I'm declaring my standard pressure to be 1 atmosphere. The volume is what I don't know. It's what I want to figure out. So B is going to be left as something I want to get alone. Right? That should be equal to N, which is our number of moles of gas, times R, which is our gas constant, and times T, which is our temperature. Okay, now here's where we need to do a little bit of thinking, because they don't just give me a number of moles in this problem. I'm going to have to figure it out, which is a little frustrating. Okay. I have to get the temperature, but if it's at standard temperature, I can just grab that number. It should be 273.15. Right? And since I picked my unit of pressure, I just have to pick my gas constant that goes with that unit of pressure. The R, the gas constant for atmospheres, is 0.0821 atmospheres liters per mole Kelvin. Okay, so everything's going all right so far, except I have two missing things here, and that's no good for algebra. Algebra is really good for finding one missing thing, not two. So I'm going to need an n to plug in here instead of just leaving it as n. So I need a way to figure out moles. Well, moles is an amount of a chemical. I'm given grams of CO2. I can convert that into moles, right? So we're doing a little bit of unit conversion, a little bit of stoichiometry is coming back. It never goes away. It never goes away. So I want to convert 16 grams of CO2 into moles. All right, 16 grams of CO2 is what I want to convert. I have to get rid of grams of CO2. So that's the unit that goes on bottom. Okay. I want to get to moles of CO2. So that's the unit that goes on top. Whenever I have moles on one side of a fraction bar but not the other, I can be 1 with moles. I want to put a 1 up on top. And then for the grams of CO2, I need to add up the mass of 1 carbon and 2 oxygens from the periodic table. All right. On the periodic table, carbon has a molar mass of 12.01. And each oxygen has a molar mass of 16. So I'm doing 2 times 16. So 12.01 plus 16 plus 16 is going to give me my molar mass down here. It should come out to be about 44.01 grams. And that is in every mole of CO2 that I have. So to figure out just exactly how many moles of CO2 I'm dealing with in this case, I need to multiply by the top and divide by the bottom. So 16 times 1 divided by 44.01. So let's punch that in. All right, that comes out to be about 0.364 moles of CO2. Okay, so now that we have our moles, we can plug everything in and solve for our volume. Okay, so our 1 atmosphere times our volume is still just going to be that on the left side. Okay. On the right side, we can start to condense these. So I'm going to take 0.3 0.364 times 0.0821 times 273.15, and that's what's going to be on this right side over here. Okay? My moles units on top here and on bottom here are going to cancel. And my units of Kelvin on top here and on the bottom here are also going to cancel. So if you like watching units, we should be left with units of atmospheres and liters on the right side. Plug this in. All right, we get 8.16-ish. And I recommend having a calculator or something with yourself when you watch these videos. Try and do it along with me so that way you can see if it makes sense or not. Sometimes it makes sense when you see it, but not when you actually go and try it for yourself. So I recommend kind of trying to follow along. Okay, so all these multiplied together, I mean 8.16. So my last thing to solve for volume is to just divide both sides by 1 atmosphere. All right, so on the left side, I totally cancel it out, so it's just V on the left. On the right side, my units of atmospheres cancel. And then 8.16 divided by 1 is just going to be 8.16. The only unit that's going to be left is going to be liters. Okay, so pretty big balloon. My volume is going to be 8.16 liters. Now there's actually a shortcut you can use on this problem and problems like it when you're dealing with looking for volume or an amount of moles when you're at STP. You might remember that at STP, at standard temperature and pressure, 1 mole of gas equals 22.4 liters of volume. Now, we don't have exactly 1 mole of gas, but that's what conversions are for. Okay? So, we can ignore the rest of the plugging in the ideal gas law since we know that we're at STP, right? And we've got this number of moles. We can convert that into a volume given those conditions. And we should come out to get the same answer. It doesn't matter which way you do it. This way is faster, but you also have to be sure you're at STP. So let's try it out. So we found out that we have 0.364 moles of CO2 going on here in this balloon. So I'm going to take that a step further. And convert it. Okay? I want to get rid of moles on bottom. So that unit will cancel out, just like how grams would cancel out here. All right, so I'm canceling moles on bottom. All right, I want to get liters of volume on top. Liters of CO2. So this conversion factor, this fraction bar here, is just asking how many of this is in this, or how many of this is in this. All right? At STP only, can't have just one or the other, got to have both standard temperature and pressure. Right? 1 mole of gas is 22.4 liters. So if I plug that in, I take 0.364 times 22.4 divided by 1 mole, I should get my answer. So let's try it. 0.364 times 22.4. Dividing by 1 doesn't do anything. And I get about 8.15. And my unit is liters. Before we got about 8.16. So that's pretty darn close. Okay? I would definitely count it for sure. Okay? So if this appeals to you, you might want to keep this in mind as an extra little kind of shortcut to make things a little bit faster.